everyone. Welcome to the lecture number 20 of this NPTEL lecture series on charging infrastructure. And in this lecture, we will study the DCM operation of boost based PFC converters. In the previous some of the lectures, we have studied the operation of boost PFC converter, which consists of a diode bridge as the first stage, diode bridge rectifier as the first stage, and then followed by a DC-DC boost converter after that. Now if you look very carefully in this particular thing, we have also seen the derivative or the bridgeless PFC based, where this is nothing but a bridgeless PFC, which is again which does not have any diode bridge rectifier. However, it is also having the same kind of functionality, which is having the kind of a boost converter system. And here if you look very carefully, in both the things, we are actually trying to control the current through the inductor, this IL here, which is nothing but the unfolded version is nothing but equal to IS, or you can say the modulus of IS is nothing but equal to IL. You can say IL is nothing but modulus of IS in this case, and here IL is nothing but equal to IS. So we are trying to control the current going through the inductor, and that's when we could able to control the current which is been drawn from the source, and we can ensure that unity power factor current is been drawn from the source by doing the closed loop control. And in the closed loop control, we have seen two things. One, obviously we have seen average current control, where we kept our switching frequency of the devices S1 and S2, and here again S1 and S2, the switching frequency of the devices are kept constant, and in the entire time we have seen that the inductor current has some average value over which there is a ripple riding over that, and that's when we can able to ensure that the switching cycle average variation is having the sinusoidal behavior, and thus we get the actual current which is having sinusoidal variation and high frequency ripple is riding over that. Now there we see that at all the times, we have assumed that at all the times the inductor current is continuous in nature. That means it goes, let us say if this is the waveform we are getting for IS. So the inductor current is actually going in some positive, having positive slope, coming down in negative slope, and it is not coming down to 0. The inductor current is always non-zero except near to zero crossing. That is again the, that's a requirement of that, but in the other than the zero crossing near, other than the time period away from the zero crossing points, you still have the inductor current which is continuous in nature. It is not going to 0. And to ensure that this is there, what we have done, we have seen the closed loop control, where we require a very important thing, which is the multiplier block. So in case of bridge boost PFC case, we have multiplied with the modulus of sin omega t, while in case of bridgeless PFC, we have directly multiplied it with unit sine signal, or you can say that sin omega t. So in both the cases, inside the controller, or let us say we are implementing that controller using the analog components, we require a multiplier block, and that particular multiplier block is sometimes causes, the huge computation burden, or you can say that sometimes you require more memory to handle that multiplier, the result of that multiplier block, and also sometimes it also, time consuming is also there. So we sometimes require a high end microcontroller to handle this multiplier block to do the multiplication, and that is why sometimes it is also called as the multiplier control approach, where you are actually sensing the sin omega t or modulus sin omega, or you are actually generating the unit sine wave sin omega t or modulus of sin omega t and multiplying it with the output of the voltage block or voltage controller block. Then along with this multiplier block, there is also one more problematic case is there, is the generation of that unit sine omega t, and that unit sine waveform, the generation of that unit sine waveform has to be such that it is closely following the actual input AC voltage. So, what you can say, there should not be any phase angle between that unit sine omega t and the Vs peak sine omega t which is been there in the grid. And we know that generally this grid voltages have variation in frequency, have also variation in voltages, and those are obviously those are maintained within the tolerances, but there is a variation. We cannot say that at every time it is the pure sine wave having Vs peak in the positive direction minus Vs peak in the negative direction. So, we cannot able to sense the exact peak, and we could not able to say that the entire frequency is actually the nominal frequency. So, that is why how we can generate the unit sine omega t waveform, and that is when it is one of the research topic to generate that unit sine waveform, or you can say the unit sine signal. And it is also very complicated because you have to make the high end PLLs, you have to do high end filter circuits, you require high end computation block to actually estimate or to actually generate that unit sine waveform. And then after doing that, we also have to do the multiplication with the output of the voltage block, which again takes good amount of memory space and also the computational effort. So, that is why sometimes either you require a very high end microcontroller, or if you wanted to do in the low end microcontroller, then you must have that required computational time available with you to actually perform that particular multiplication. That means sensing the actual voltage signal, and then from the actual grid voltage you have to generate the unit sine, either unit sine omega t or modulus of unit sine omega t, or modulus of unit sine signal or sine signal, and then multiply it with the output of voltage controller block. So, doing those things are very complicated, require computation, you require high performance microcontroller to do those computation. Now, to avoid those things, one can also do one simple, one voltage follower approach, where instead of making this inductor current having the continuous conduction mode, we can make sure the inductor current will have the, we can ensure that inductor current is following the your input voltage, and making sure that you do not require any multiplier block. So, to do that, one way by which it can be done is making sure this converter operates in a, this system operates in a discontinuous conduction mode. So, let us try to understand what is discontinuous conduction mode of boost PFC. Now, in discontinuous conduction mode, we know that our in this particular circuit our Vd is nothing but modulus of Vs, and we can also know that our Is, or the current drawn from the grid, is nothing but equal to IL when Vs is greater than 0 and equal to minus IL when Vs is less than 0. So, in other words, if we can able to know the IL value, we could able to say what kind of input current we can expect to be drawn from the source. Now, let us try to see how our discontinuous conduction looks like. So, let us take for some of the one or two cycles, one of the let us take in one of the switching cycle, say TS switching cycle. Let us say my inductor current which is there, since we have a discontinuous conduction mode, that means the inductor current is going to 0 in every switching cycle, and it starts from 0 in at the start of the switching cycle whenever the positive voltage is applied across the inductor. So, if we assume that it starts from 0, if the inductor current starts from 0, it goes to its some peak value let us say define this as, let us say I peak, we can say, and then this particular current. So, this is the case, at this point you can say that, let us say define this point as TS1 on, where at that TS1 on my switch S1 is on, because whenever the S1 is on, you are directly applying Vs voltage across this inductor, you will have the positive slope. And then after TS1 on duration, this switch S1 is switched off and S2 is on, and that is when you will start applying Vs minus V0 voltage across this VL, and since V0 is greater than Vs peak, so we are applying a negative voltage across this inductor, and that is when inductor current falls down. And since we are talking about discontinuous conduction mode, we will ensure that this inductor current goes to 0. Now this time, let us define this time as TS2 on. And then let us say from this point to this point there is no current flowing through the inductor, and that is when there is no instantaneous current drawn from the source during that time. And then again after this Ts duration, one of the switching cycle, we see that again my inductor current will again, S1 is on, and then again we will have this, maybe some different I peak will be there, we will see what could be the peak, and then again it falls down, again 0, and then again it goes up. So that kind of waveform is there. So now let us see in that particular Ts duration what are the voltages which are applied and how that voltage and currents are dependent on each other. So if we look very carefully, in this case when it is going from 0 to Ip, so we can write down VL is nothing but L di by dt. So di is always going from 0 to I peak, so we can say I peak, L I peak divided by dt, which is nothing but TS1 on, is nothing but equal to VL. And during TS1 on duration, whenever the switch S1 is on, you are only applying Vs. So you are applying the Vs voltage across this, and that you can write down this Vs is nothing but equal to L Ip by TS1. And we know that I can write I peak is nothing but, this Vs is nothing but a Vd, which is nothing but modulus Vs. So we can say modulus Vs, and this is nothing but Ip is nothing but modulus Vs Ts1 on by L. And if we make sure, if we can ensure that our Ts1 on is constant, then we can say that if Ts1 on is constant, then the peak current or the peak of the IL current, I peak, which is peak of inductor current, follows the modulus of Vs variation, or you can say that your AC voltage. So we can see that our peak value, peak inductor current is following nothing but the input Vd, which is nothing but the modulus of the Vs. So we can say that our peak is varying sinusoidal in nature, same as that of the AC voltage, however with different amplitude, but it is varying in the peak is varying in the sinusoidal manner. So Ip is varying in sinusoidal manner. Thus we can say that the input current peak is following the input AC voltage. Further, if peak is following the voltage, then there is a possibility that the average variation of current in a switching cycle is also following the input AC voltage. And if that thing happens, then I do not need any multiplication on any high computational burden blocks, and thus can able to ensure that my converter is actually following the voltage, or you can say the converter is operating in the voltage follower mode. And we know that our input voltage is varying sinusoidally, so the current which is been drawn is also following the input AC voltage. So let us take our discussion ahead, where so we know that my IP is always varies with the modulus of Vs, and let us try to calculate the average variation of IL. So let us calculate average variation over the Ts period, that average variation over the Ts period we can write down. If we know that we are actually having this kind of variation, so every time it start from 0 goes to this IP value, obviously this IP value varies with the input voltage, but it goes to IP value and then again comes back to 0. So we can say that during this time I can just write the average value is nothing but, so we can write half into, so we can take half times, we can write modulus Vs times T Ts1 on by L multiplied by Ts1 on plus Ts2 on divided by Ts. This we can write down because you know this is Ts1 and Ts2 and divided by Ts we can write. Now we can just take let D1 is equals to Ts1 on by Ts and D2 is nothing but Ts2 on by Ts. So we can write down the average variation of inductor current over Ts duration is nothing but half modulus Vs of t, or just same, just Vs of t Ts1 on by L times D1 plus D2, and I can also write Ts1 on as nothing but modulus Vs of t as nothing but D1 Ts by L D1 plus D2, this is ILT average over Ts duration. Let us define this as equation number 1. Similarly, we can also see, since the current goes from 0 to the top and then coming back to 0, so we can also apply volt second balance in this case. Volt second balance, we can say that my modulus Vs of t during D1 of Ts plus I can write modulus Vs of t minus V naught D2 of Ts, and that we can make it equal to 0, and that we can define D2 is nothing but modulus Vs of t by V naught minus modulus Vs of t times D1. Now this I'll define this as 2. Now this we can put our D2 value in this expression 1. So we can write or substitute 2 in 1. We can substitute 2 in 1, and we can finally we can write down L of t average during the Ts duration is nothing but half D1 plus S of Vs of t V naught minus Vs of t modulus T1, and this we can write IL of t average during Ts duration is nothing but half modulus Vs of t time this d1 we can take it out, d1 is square ts, this is d1 square ts, and this when we do this thing v0 minus Vs omega Vs t goes up, Vs modulus Vs t cancels out, and it will be nothing but v0 by v0 minus modulus of Vs t. This we will get the expression. So this is we got as the average value of this thing, and we know that our Is of t is nothing but equal to, you can say that IL of t when Vs is greater than 0 and equal to minus IL of t when Vs is less than 0. So we have Is is nothing but equal to IL of t greater for Vs greater than 0 and minus IL of t for Vs less than 0. So if we look very carefully, my this modulus of Vs which we are getting the average variation as modulus of Vs of t. So this we can, if we are writing for Is, so we can write down that average variation of Is during the Ts duration is nothing but half multiplied by Vs peak sin omega t d1 square ts v0 by v0 minus Vs peak sin omega t the modulus. Sorry, I have missed the modulus sign here. So we see that this average variation of Is of t is varying in sinusoidally if, and in this if we keep d1 and ts constant, that means the ts1 is kept constant. So we can ensure that average variation of IL of t in the switching cycle is actually varies with that this variation is sinusoidal in nature. So if we see this waveform, what we will see is that, let us say our Vs is having something like this. This is my Vs, or let us say modulus Vs. In one half cycle only we will see. So my this variation, you will have positive coming to 0, then goes down, then positive coming to 0, then 0, then positive coming to 0, 0, positive coming to 0, for some time it is 0, positive coming to 0, like this. So if we see that average variation will be having something like this, we will get the average variation, and this is your nothing but, since our this is nothing but IL, this is nothing but your IL, and if we see the peak of IL is actually varying sinusoidally, having the maximum value at the peak of the modulus Vs, and if we see this is the average variation, this is the IL average variation over Ts, and this is close to sinusoidal. It is not actual sinusoidal, but it is close to sinusoidal. It is slightly away from sinusoidal, but however the variation is of a sinusoidal behavior, but it is not exactly sin omega t or actual sinusoidal variation. However, the variation is looking close to sinusoidal in nature. It is primarily because you have modulus Vs peak sin omega t also at the bottom. So because of that, we have switching cycle average variation closer to sinusoidal and not exactly sinusoidal. However, the peak current is varying sinusoidal in nature. and we are not requiring any multiplier block or any sense or generation of this unit sine omega t block. So the advantages with this, what we will get, if we try to see the closed loop solution further, the closed loop solution will be very simple. You just sense the output voltage, you just define V naught reference output through the controller, directly it goes to the modulator block, where we make sure that the turn on period of this S1 is kept constant and the switching frequency is kept constant. That means turn on time of S2 is varied accordingly, and that is when this modulation will give you this modulator will give the output as PWM of S1 and PWM of S2 switches. So here you are not requiring any multiplier block, you do not require any generation of sine omega t block, also you do not need to have any closed loop current control block as well. Automatically the current which is being drawn from the source is actually following the AC input voltage or AC voltage. So the advantages what we get is that with this particular setup is the current drawn from the source, the current drawn from the source follows this the AC voltage automatically, and the use of multiplier, dual loop, and the unit sine omega t waveform can be avoided. Okay. Also one more advantage you will get, see if you look very carefully at every instance of time, whenever the S1 is on and whenever the S2 is turning off, at that time the current, the IL current is 0. So that means you will also have reduced switching losses, reduced switching losses, because whenever you are turning on this S1, it is turning on with 0 current, and whenever the S2 is turning off, it is turning off with 0 current. And if let us say instead of S2 if one is using diode, so the reverse recovery losses is nearly 0 in case of DCM operation of the boost PFC case. So that is again one advantage we will have. So I mean reduced switching loss or lower switching loss if we are using active switch, or if diode is used in place of S2, the reverse recovery of diode is nearly 0, because it is turning off with 0 current. Now the disadvantage of this thing is, the disadvantages of this topology is obviously the input, I mean the switched average variation of current, or you can say the average input current is close to sinusoidal and not actually a sinusoidal. So you will see the TSD is more in this. Second, we will also see that since the peak is varying sinusoidally as well as the average is not sinusoidal, is close to sinusoidal. So what you can see is that the ripple is more, and because the ripple is more, you can see that the inductor current ripple and the switches have higher RMS currents. So RMS current of S1, S2, L, D1, D2, D3, D4 are more. And you will also see one more important thing when it is switching off. So you can see that at this point my S1 is on, at this point my S2 is on. So you will see that the S2 switches on with the higher currents. So or you can see that S1, here the S1 turns off and S2 turns on. So you can say that the S1 turns off with higher current, S1 turns off with higher current. Thus, I mean sometimes have more switching loss, or we need to ensure that gate driver or the parasitics does not get activated because of that. So this is the advantage with this DCM operation or discontinuous conduction operation of this boost PFC, which is we can automatically make sure that the current drawn from the source is actually following the AC voltage source, and the peak of current is actually varying sinusoidally. However, the average current is not sinusoidal but is close to sinusoidal, having, which indicates it is having higher TSD as compared to the continuous conduction mode, because there we have the fundamental component and then the switching frequency component, and switching frequency component is very far away as compared to the fundamental component. Then we see that our ripples are in this one are more, and that is when the RMS current of these devices are particularly more. And one more advantage we will get, because the DCM, if my S2 switch is, you obtain the realize this S2 switch with diode, we can see that diode turns off with the very less reverse recovery losses, or reverse recovery losses of diode is nearly 0. Reverse recovery losses of diode is nearly 0. And one more thing we will see, the when doing the closed loop operation, we do not need any dual loop structure, we do not need any multiplication factor, or we do not need any unit sine wave form generation. Here we just need the one loop where we ensure that output is actually following the reference, whatever we set the output voltage reference, because automatically the current drawn will be following the voltage. So this is the advantage we get by the DCM operation of the boost PFC converter. Thank you patiently for listening to this lecture.